Thank you all for spending your evening coming to something like this. I appreciate it. So let me, now, as you know, every talk on modern programming has to mention Moore's Law. It's a kind of a requirement, so I'm going to do this at the very beginning. Now, not so long ago, when you would buy a laptop or a server, every year it would be faster. The clock would run maybe twice as fast every year. And this was great for people who wrote software because you could add new features to your software and it would slow everything down, and 6 months later no one would notice because the processors had become faster. Then around 2000 that stopped. As you can see, the clock speed, the blue line on the bottom, went up and up and up, and then it went flat. It stopped improving. The transistor size continues to shrink. So the reason the clock speed is unable to keep up with the transistor size is simple. It's because they overheat. As the transistors get smaller and smaller, if you try to speed up the clock, then it gets too hot. So as a result, computers are basically the same speed this year as they were last year. The difference is that when you go and buy a laptop, you get more of them. So this year you can get 4 cores, next year you get 8 cores, next year you get 16 cores. And the wonderful thing about this is that people don't really know how to make use of this, which is why people like me still have a job. So a long time ago, computers consisted of a single CPU and some memory. This was called a uniprocessor. This was back in the age of the dinosaurs. After that, people built shared memory multiprocessors. These were separate chips that had processors and separate memory chips that were connected by some kind of a bus or communication line. Today, what everyone builds is what's called a multicore processor. Here you have multiple chips on multiple processors on the same chip. So the processors, memory caches are all together. And what this looks like is, what this looks like is something like this. The little rectangles at the bottom are the processors. Everything else is interconnect and memory. Now, what's different about this is that, as I mentioned in the old days, every year your processors will get more powerful. I show them here as being bigger, but in fact they're smaller. But every year the processors would get more powerful and the speed of your software would increase. Now, in an ideal world where processors don't get faster, but you have more of them, then the same thing should happen. You would like to say, well, if I go from 4 processors to 8 processors, then I can get twice as much work done. But, of course, it's not really that simple. What actually happens is that when you introduce more processors, you spend more time and energy on synchronization and coordination. And if you're not careful, you spend so much time on synchronization and coordination that you get basically no speed up. And this is the big danger that happens when you try to move to more and more concurrent processors. So parallelization and synchronization are difficult. And if any of you have ever tried to do this, no doubt you're aware of this. So one way to talk about this is something called Amdahl's law. So we can define the speed up that you get by moving from a small number of cores to a large number of cores as the ratio of the execution time with one thread versus the execution time with all of your threads. Now, I want to warn you that people talk a lot about Amdahl's law, and it's always written as a mathematical formula. But it isn't really a mathematical formula, because actual execution times depend on much more complicated things. But this is a useful way to talk about things. So as long as you don't take this too seriously or too literally, then this is a useful way to think about parallelism. So we can write a formula for speed up in the following somewhat simplistic way. So we have our application, and some parts of our application are easy to make parallel. These are things that require no coordination, no synchronization. I can draw this part of the picture at the same time that I'm drawing that part of the picture without any kind of synchronization. So we'll say that P is the parallel fraction. This is the part of the program that is easy to parallelize. We can take that part and divide it evenly among all the processes, so the time it takes is P divided by N. That's the ideal simplified vision of the world. And the remainder is a sequential part. So the sequential part is the part that is not parallel, either because it cannot be made parallel for engineering or mathematical reasons, or because it's a lot of work to make things parallel and nobody bothered to do this. Now, there are a number of implications of this here. The main implication is that if your synchronization is bad, then nothing else is going to work. That the cost of synchronization and coordination will easily dominate everything else. And so in order to make this more concrete, I'll walk through a few very simple examples. So let's say that your boss goes out and he buys a 10-core machine and calls you in and says, okay, your job is to make me look smart for having bought this machine. I want you to take our application and I want you to get a 10-fold speed up. And if you don't succeed, well, things could go badly. So your job is now to take your 10-core machine and get a 10-fold speed up from your software. So now you look at your software and you say, no problem. 60% of my application is easily parallelizable. So most of it is parallel. The majority of lines of code can be executed in parallel pieces. Only 40% of this is sequential. So how close to a 10-fold speed up will this give you? Well, it turns out not very much. So now you have to go to your boss and say, well, you know that expensive 10-core machine that you bought? Well, we managed to double our speed up. I don't think that would look very good. Your boss will not be happy with you with this. So you go back to your programmers and you say, make this more parallel. Go over it, refactor the code, do everything you need to do to make things go faster. And they come back after staying up late all night, working all weekend, and they said, now we made things 80% parallel. Can we go home now? And so how much speed up do you get with an 80% concurrent program? Well, not even 4-fold speed up. So this is starting to look very, very tough. So even if your program is 80% parallel and only 20% sequential, you only get 3.5 times speed up on a parallel machine. So let's go back and force the programmers to do even more work. And then they come back and say, we finally made this 90% parallel. And I think you get the message. At 90%, you have 5-fold speed up. If you make it 99%, then you'll get 9-fold speed up, which is close enough. So the lesson here is not that it's impossible to exploit parallelism. It's that you have to be very careful how you do this. And in particular, the small amount of programming that you do that concerns coordination, synchronization, locks, compare and swap, all these things, turns out to be very important if you want to get speed up out of parallel machines. that even a little bit of bad synchronization is going to cause problems. So the analogy, sorry, I have a cold. The analogy here is that you can go out and you can buy an Italian racing bicycle with a graphite frame and hollowed out parts to make it super light and super fast. But if the ball bearings, the parts where the pieces move together, if those aren't any good, then it doesn't matter how good the rest of your bicycle is, because it's not going to go very fast. And so what I want to talk about here are the ball bearings of your concurrent software. These are the pieces where different parts of your code grind together. And this may be only a small part of your code, but it is extremely important to have that work in order to make your programs run fast. Okay, so let's talk about how traditional ways of doing synchronization. So the usual, the usual way that people do synchronization on concurrent data structures is you put a lock on it. So a lock is like the lock on a bathroom. A thread comes in, you lock the data structure, you can do anything you want, and no one else can get in, and then when you're done, you unlock it. This is something that we teach undergraduates. It's the basis for Java synchronized blocks and synchronized methods, basis for monitors. It is so common that until recently, people hardly even questioned it. You know, it was considered the one thing that everybody is supposed to do. You could never get in trouble if you did it, because what else could you be doing? But I'm going to raise some questions about whether this makes sense. So the easiest way to lock a data structure is you put one great big lock on everything. Now, as some of you may know, for many years, the Solaris kernel had a single lock that controlled the entire thing. This was okay because nobody had multiprocessors, or at least not enough for Sun to care about. And in fact, the lock grew up by convention. It wasn't part of the original design, but a convention arose inside Sun that the people worked on the kernel. There was one bit in a field where you could set it and be reasonably sure that no one would interfere with what you're doing. Now, after a while, Sun realized that this was not a good idea, because people were starting to buy multiprocessors, and they were getting no scalability. Every time you make a kernel call, everything would slow down enormously. But they were too frightened to change it, because nobody knew what would happen if you tried to take the kernel and break it into smaller pieces. And it took them 2 or 3 years to come up with a multi-threaded kernel. So the use of a single lock can be tempting because it's easy to convince yourself it's correct. And it's easy to get even the most novice programmer to use it. If there's any danger, any doubt, just get that lock and you'll be safe. You won't be very fast, but you'll be safe. But the problem is, of course, that you're going to get terrible performance. And every year when your clients buy larger and larger multicores, they're not going to see any speed up. So the answer is, it's easily made correct, but it's not scalable. So we don't really like large monolithic locks. So a natural follow-on is to say, well, let's break up our data structure, our kernel, our file system into lots of little pieces, and we'll put separate locks on each one. And when you want to operate on the data structure, you acquire only the locks that you need. So if I'm working on this part of the object and you're working on that part of the object, we each get our own separate locks, and we can go run concurrently in peace. Now, if you've ever tried this, you'll notice that you have, unless you are a much, much better programmer than most of the human beings on this planet, you're going to run into all kinds of mysterious bugs, deadlocks, very difficult problems, because it is really hard to write fine-grained locking, programs that use fine-grained locking. When I teach I have a course that I teach to undergraduates on how to do concurrent data structures. And sometimes I can't resist. I will present a very reasonable looking algorithm that uses multiple locks that has a bug. And I'll present this, and then I'll ask the students, does this look correct to you? And some of them will be foolish enough to say yes. And then I'll say, aha, no. Here's the bug. And some of these bugs are extremely subtle, but extremely dangerous. Because they might not happen for a long time. When they do happen, it can be very hard to reconstruct what happens. Because if you have a synchronization error, then one data structure will become quietly corrupted, and then another will become corrupted, and then this will spread. And then 5 minutes later, everything will crash, and it will be very difficult to understand what happened. Locks have another problem. So locks are not robust. So if a thread that's holding a lock is delayed or it crashes, then other threads that are perfectly capable of doing work can't do anything. It's like having a 2-year-old walk into a bathroom, lock the door, and fall asleep. Nothing people out on the outside can do will help. Now, you might say, well, actually, threads don't crash all that often. But in practice, threads don't need to crash. A thread that takes a cache miss is delayed for hundreds of cycles. A thread that takes a page miss is delayed for thousands or tens of thousands of cycles. And so your programs lead a very dangerous life because any thread can be suddenly delayed without warning for a very long period of time, which is not much different from a crash. You don't really want to wait for 100,000 cycles for a thread to fix a page fault while it's holding a lock. And this is often a particularly bad problem in practice because if the number of threads is less than the number of hardware cores, then this doesn't happen much. But as soon as you have more threads than hardware cores, then this will happen all the time. And so what happens is that your software will perform wonderfully until you make that n plus first thread. And then things suddenly start to seize up. And you're not quite sure why. So if the thread holding the lock is delayed, no one else can make progress. Now I'm still not done explaining what's wrong with locks. So another problem with locks is that the relation between the lock data, that byte in memory that tells you whether the lock is free, and the object that it controls exists really only in the mind of the programmer. Now, I know that, for example, Java has an implicit monitor lock associated with each object, but that really doesn't work all that well, because sooner or later you want to do something that doesn't fit this model, so you need to go to the Java concurrency library and use their locks and then do your own synchronization. And what happens is you end up developing these fairly complicated protocols that everyone in your group is required to follow. And most of the problems with synchronization happen because people misunderstand these protocols. They change something where the protocol is no longer absolutely correct. And for example, a friend of mine pointed out this wonderful comment from the Linux kernel. Now, don't spend too much time trying to read it. Just sit back and enjoy its beauty. So basically, I have no idea what this means. I don't know if anybody has any idea what this means, but I know that if I were working on this data structure, I would be very uncomfortable. Because I don't know whether this is true. I don't know who wrote this. Maybe some Finnish teenager in 1995 wrote this. Is it still true? Was it ever true? What happens if I don't follow this? Now, building complex software systems on the basis of cryptic comments is not really a serious engineering discipline. This is not the way we want to build our planes, our civilization, and so on, because it's inevitably going to break. Even if it was done perfectly back in 1995, it's going to break at some point. There's another issue which is hard to quantify in a scientific sense, but I think everybody understands this intuitively, and that is that simple problems, simple synchronization problems that you can explain to any high school student are actually quite difficult to solve. For example, here is a double-ended queue. A double-ended queue is a data structure where I can enqueue or dequeue from either end. This is a natural data structure for many applications. So here I have one thread is enqueuing at one end and one thread is enqueuing at the other end, and I want these to happen concurrently. And in fact, I want these to happen as concurrently as possible in some sense. So what I want to say is that if the ends of the queue are far apart, then the blue thread and the red thread should be able to proceed without synchronization because they don't affect one another. I don't want them contending for a lock because there's no need. And plus, I believe that this is perhaps the most common case. So 99% of the time, the ends of the queue are far apart, and I don't want to pay for synchronization that isn't necessary if the case where it is not necessary is extremely common. Now, if the queue is very small, if there's only one element in the queue, or if the queue is empty, then it is necessary for red and blue here to synchronize. If there's only one element in the queue and both threads try to dequeue it, they have to decide who gets it. They can't both get it. And so I want to say if the queue is small, then synchronization is okay because it's necessary and it's rare. If the queue is large, then I don't want synchronization because it's expensive and unnecessary. And my boss will fire me because the double-ended queue application is slow. Now, what's alarming about this is that if you have a nice, clean solution to this, you could probably publish it in an academic conference. And I know this because a clean solution was published in the main conference in distributed computing, back in 1997. So if you come up with a new solution, you can probably publish it, maybe not in the best conference, but maybe in a second-tier conference. Now, what's alarming about this is that the problem is very simple. Everybody here understood what the problem is, what the motivation is. You're probably thinking right now that you know how to solve it. You're probably wrong. I don't know. But it's alarming that very simple problems have very hard solutions. Now, if you talk to our friends in mathematics, they have very simple problems that take centuries to solve. Fermat's last conjecture, Goldbach's conjecture, all of these. And they're very proud of this. You ask them about this and they say, aha, this demonstrates the superiority of mathematics over computer science as a spiritual discipline that we can come up with these problems. But the response is that computer science is not mathematics, it's an engineering discipline and we're trying to do useful things. And if we can't come up with simple solutions to simple problems, then how are we going to solve the more complicated problems that face us every day? Okay, then the next issue that I want to talk about is composition. Now, composition is something that, as software people, you know a lot about. So one thing that we tell our first-year students, probably we tell our high school students this, is that if you're writing a program, you do not need to write your own sine and cosine programs. If you want to compute sine and cosine, we have libraries. We have libraries written by experts. You don't have to sit down and learn about Taylor series and floating point precisions and where each bit goes to write a good sine and cosine program. You just call a library. And moreover, any program you write can call this library. It doesn't matter, the context where you call this program doesn't matter because it's a kind of a black box. Now, there's a kind of a theme in modern concurrent computing, which I talk about a lot when I teach this in a year-long course, and I'm only going to be able to mention it a few times here, is that this is a very young and immature field, and most of the abstractions are broken, in the sense that you can't really understand how to use high-level things unless you understand how the low-level things work, because things are going to break in ways that will not make sense unless you understand the lower-level pieces. When you use a laptop or a server, you don't need to pay attention to the fact there's virtual memory, that pages are being moved in and out of memory quietly while you're using the computer. Unless you're very, very performance sensitive, the abstraction of virtual memory hides all of the complicated and ugly details. Same for garbage collection. In the old days, when your program would start to garbage collect, you would go out and get some coffee and then come back because it took so long. Now garbage collection happens in the background and you don't need to see it. Unfortunately, in concurrent world, we're not there yet. So the first thing that I would like to do is I would like to take, for example, two concurrent queues and compose their operations. So here I have one queue on top and one queue on the bottom, and I want to take an item from the first queue and move it to the second queue. Seems simple enough, but I want to do this atomically. I don't want to see 2 copies of an item. I don't want to see 0 copies of the item. When I look at the queues, I want to see that that item that I'm moving is either in the old queue or the new queue. I don't want to see any intermediate states. And this is something when we call sine and cosine routines, we don't even think about this. We probably never even notice the fact that you can call these routines, you can compose sine and cosine to get tangent without worrying about the context where you do this. But there's no easy way to do something as simple as an atomic transfer from one queue to another in most lock-based languages. For example, suppose I write a Java data type to do this. Well, here's what I really want. What I really want is I want to lock the source. So I lock the first queue, then I lock the second queue, then I do the transfer, and then I release the locks. Now, if you try to do this with Java synchronized methods, then it doesn't work. Because when I call the synchronized method, it acquires the lock on the way in and releases the lock on the way out. So there is no way that I can hold the lock after I dequeue. After I dequeue the item from the first queue, I've released all my locks. Now, I don't mean to disparage this design because it's actually, in many cases, a good design. You want to keep synchronization mechanisms inside the object, not outside the object. In this case, that doesn't work. So we have to export maybe a lock and unlock method from the queues. But if you do that, then that's a software engineering disaster, because now you're relying on the clients of your objects to follow protocols and to behave themselves. And if one of your clients forgets to release a lock, then 5 minutes later your system will deadlock. And they'll blame you. So for modularity reasons, we want to put synchronization inside methods. For reasons of expressive power, we want to export synchronization. And there really isn't an easy way to resolve this. So having clients in charge of following complicated protocols to keep your entire system healthy is not a very good idea. And the abstraction here is broken. So these are the complaints that I have about traditional lock-based approaches. Now, I should mention that of course, there are times when locks do exactly what you want. I'm not proposing a radical elimination of all locks, But there are many cases where current locking disciplines, current locking structures just don't work. And trying to make them work is going to just make your systems worse. So instead, I'm going to propose something we call the Transactional Manifesto. I understand St. Petersburg is a great place for manifestos and revolutions and things of that nature. So the idea here, the basic idea here is very simple. And this is kind of a secret, which makes some people angry when you tell it, but it's really true, that almost all of the important ideas in systems came from databases. In particular, they came from a series of database systems developed by IBM back in the 1980s, called System R. But the people who did this, they didn't publish many papers, but they wrote a lot of technical reports. And they wrote these technical reports using IBM's kind of internal technical language, which nobody today understands. It's like Sanskrit or Old Church Slavonic. You know, it's an ancient language that nobody can read. So if you can understand what they say, you can steal their ideas, and nobody knows where they came from. So the idea that we are going to steal here is the notion of an atomic transaction. Atomic transactions are central to databases, for example, but we're going to take this idea and we're going to change it in subtle ways. Now, sometimes this causes confusion because the multi-core transactions and database transactions are not exactly the same. They're similar enough that we can use the same name, but don't assume that they're exactly the same because that could lead to problems. So the basic idea is that much of what we do today is inadequate for multicores. Why didn't we fix this before? Well, that's because multicores are still relatively new. It didn't matter if you had bad concurrency control back when there were no multicores because nobody cared. But now lots of things depend on being able to use multicores, and it's time to rethink what we're doing. So our agenda is to replace a locking API with a transactional API. And I'll explain what that means soon. We want to design languages and libraries that support this. Now, actually, I'm not going to say too much about languages here because introducing transactions into languages is still a very immature field. And most of this is currently done in C and C++. There's been some work in putting transactions inside various Java virtual machines. And there's been some work about putting transactions into Java, but it's really a very immature state. So there's probably less Java in this talk than you're used to. But maybe you can go out and fix things so that there will be more. And one issue that I usually talk a lot about, but I'm not going to have time to talk about, are tricks for making transactions run quickly. A very short story here is that in databases, people who design databases have lots of experience writing atomic transactions and writing implementations of atomic transactions. But databases live on a disk, and disks are still very slow. So it doesn't matter how slow your transactional code is if you're waiting for a disk. And for this reason, database people never saw any need to optimize the transactional parts of the code because I'm waiting for 100 milliseconds for a disk. Who cares how many microseconds I waste managing locks? Now, transactional memory here doesn't have a disk. It doesn't give you any persistence properties. So every sin that you commit is visible because you're not hiding behind a slow device. Okay, so the roadmap, I'm going to explain what transactional memory is. Then I'm going to talk about hardware transactional memory, how this is currently implemented in hardware. And I'm doing this not because I expect you to turn into hardware engineers. I know that you all do software. but because, as I said before, the abstractions are broken. So unless you understand how the hardware works, you're not going to really understand why the software behaves the way it does. You're not going to really understand how things can go wrong, because if you don't know what caches are, you're not going to understand why your performance was bad, et cetera, et cetera. So this is a situation where someday I hope to be able to give this talk without talking about hardware. But to be honest, I need to talk about hardware in order to make everything else completely understandable. Then I'll talk about hybrid transactional memory. Hybrid transactional memory is a mixture of hardware and software, where we put a software wrapper around the raw hardware to make it easier to use. This does not fix all of the problems with hardware. It doesn't sand the rough edges, but it makes things a little bit better. And then finally, I'll talk about programming language support. This will be a combination of what kinds of techniques you need to implement this. What are the semantic questions? You know, what happens in this situation? What do you want to happen in that situation? How can you implement that behavior? How expensive is it? Those kinds of questions. So first, I'll talk about what transactional memory is. So a transaction, for our purposes, is just a block of code, kind of like a synchronized block in Java, that appears to happen instantaneously. Now, a synchronized block in Java kind of appears to happen instantaneously, except that there are many ways you can violate this property. But for our purposes, a transaction is multiple lines of code that just happen. Nobody ever sees an intermediate state. One way to say this is that the transactions are serializable, in that it appears that all transactions happened in one-at-a-time order. Now, of course, this is an illusion because we try very hard to make sure that the transactions happen in parallel, concurrently. But the semantics, the meaning, is that they act as if they happened in one-at-a-time order, because it's easier to think about things that way. If you had to worry about all the different ways that your lines of code could interleave, then it would be very hard to write any kind of reliable software. So what we're going to say is I can take multiple statements, put them in a transaction, and it appears as if they were one atomic step. Often we're going to do this in what's called a speculative way. So we're going to execute the transaction in a kind of temporary, partial, indecisive way. And then at the end, we're going to say, is everything okay? And if everything is okay, then we'll commit the transaction. That means that we'll make its effects permanent. Its effects will be visible to everyone. So commit something is an irrevocable act where you make plans and then you finally do something. Like, pulling the trigger is committing. If you don't commit, if you discover that you're in a deadlock, if you discover that there's a synchronization conflict, for any reason whatsoever, you can abort the transaction, which means that you take its partial effects and you undo them. You roll them back and discard them, so it appears as if nothing ever happened. So here's an example of very simple atomic blocks. So I'm going to represent a transaction with an atomic keyword, much like a synchronized keyword in Java. There's no reference to any lock. It just says that this is atomic. It doesn't specify how these statements are made atomic. It simply says, make these things atomic and let the runtime system worry about it. And here, for example, I remove a 3 from a set. I add 3 to a set. And down here, I concurrently set y to a null. And the idea is that if these are inside an atomic block, then there's no data race. It's not an unsynchronized access. Now, you remember the double-ended queue that I mentioned. I was talking about how building a double-ended queue is surprisingly difficult. So here is how you would go about doing this in a transactional model. So first, you write the sequential code. So this is how you would write a sequential double-ended code in a language like Java. And then step two, you take that and you enclose it in an atomic block. And that says if you do this on all of your methods, then you now have a thread-safe concurrent atomic block. If your language implementation is correct, it will avoid deadlocks, it will avoid unnecessary locking, and do all of these, avoid all the bad things and do all the good things. Of course, how to implement that is non-trivial, but our first step is to separate specifying the synchronization properties you want from the implementation of the synchronization properties. The specification is very simple, the implementation can be complicated. Now, I want to warn you also that I'm going to simplify many things because I don't have time to go into complicated things. So everything that I'm going to tell you is essentially true, but I'm going to skip over certain complexities, and I'm going to express some opinions as if they were obvious, even though I have friends who will argue with me about this. So you should believe most of what I say, and if something seems wrong, it's probably because I didn't have time to tell you the complete, complicated truth. So it's not always as simple. There are issues like how do you do conditional waits? So, for example, in the monitor, you can do wait and signal. Java provides, notify, sorry, notify and wait statements. You can do this in transactions in interesting ways. I'm not going to have time to talk about that. There's a question of how do you, it's possible to write programs that are transaction unfriendly, that introduce all kinds of conflicts that don't need to be there. In order to write efficient code, you need to know something about how things work underneath so you don't cause synchronization conflicts that are unnecessary. And here too, there's a lot of work has been done on this, but I won't have time to really talk about that in detail. Resource limits, I will actually talk about that a little bit. Resource limits mean it's another kind of performance issues where you could write a program that looks like it should work fine, but it doesn't work fine, and the reason is it uses too many resources. And in order to write the program that does work, you need to, again, understand how the underlying resources work. It's similar to writing a program that, in a garbage collected language, it might be easier to write a program that generates lots and lots of temporary variables, which causes the garbage collector to work too hard, which slows down your program. This is somewhat the same thing. But the claim is that what I'm proposing here takes your old problems and replaces them with new problems, but the new problems are better problems to have. You can decide at the end of this talk whether you believe me. Okay, remember our composition problem. I have one queue and I want to move something atomically from one queue to the other queue in such a way that no concurrent thread sees an intermediate state. So this code is actually trivial. I just dequeue from one queue, enqueue on the other one, and I put the entire thing inside an atomic block. And that guarantees that no other thread can observe an intermediate state with 2 copies or with 0 copies. So, clearly this is a trivial program. It's a trivial program that addresses what should be a trivial problem, but as I hope I convinced you earlier, this is not a trivial problem if you try to do this in modern Java or C# or C++ or any of these other kinds of languages. Okay, so now I've told you what transactional memory is. The next topic is hardware transactional memory. And so the question is, should I take, where is Alexei? Should I keep going or should I give everyone a break? Okay, I'll do one more topic and then I'll give people some relief. Okay, so hardware transactional memory. Again, I'm explaining how the hardware works so that you can understand later why the software is so complicated. Okay, now, first, a little bit of background. This isn't technical. This is just meant to catch your interest. Now, I can see that most of you here don't remember 1993. In fact, most of you probably didn't exist in 1993. But it's interesting to think back on the world the way it was back then. So these people were in charge of the world at the time. I will be silent on whether things have gotten better or worse since then. The main hardware platform that people used was the Intel Pentium. Not Pentium 2, Pentium 3, it was just the Pentium because it was the only one. Everything else came later, and this was the first i86 architecture ever. There was that year, the World Wide Web was invented. And the only software you could use, the only browser that existed was this Mosaic browser. And there was a vigorous debate about whether the World Wide Web was just a fad or whether it was actually going to survive. And many of my colleagues thought it was going to, it was of no importance and was going to go away. But that was also the year that we wrote a paper describing hardware transactional memory as a kind of theoretical concept. So we said, here is some architecture support for atomic transactions actually in hardware. And we said, well, this is actually surprisingly easy to do given what hardware already does. And at the time I did this, I worked for a company called Digital Equipment Corporation. And I tried to convince, they were working on something called the Alpha chip at the time, which was one of the first big RISC processors. And I tried to convince them that this was a good idea. And they said, well, how much money will we make if we put this in the chip? And of course, I had no idea because this was something new, so they didn't put it in. But 20 years later, Intel and IBM picked up the idea. And why did it take 20 years? Well, it always takes a long time to go from academic work to practice. It was also the case that in 1993, there were no multicores. So transactional memory solved a problem that nobody had. And so we would publish papers saying that someday someday concurrency will be an important and difficult problem. And of course, no one was more surprised than we were when that actually came true. But right now, you can find hardware transactional memory in Intel processors and in IBM Power Series and a few others. And the basic idea is that we're going to exploit standard cache coherence protocols. I'll explain what cache coherence is in a minute. But cache coherence protocols have two nice properties that we can use. One is they detect synchronization conflicts. If you write something and I read it, then the cache coherence protocol will detect this and do the correct thing. It also, if you have a cached copy of a piece of data and somebody modifies it, it will invalidate it. It will tell you, be careful, that data that you have there is no longer good. So here is what a standard cache coherence protocol does. Of course, what I'm describing here is very, very simplified. And what happens in real life is much more complicated, but the basic idea is the same. So we start out with random access memory that is very far away from the processor. You can think of yourself as a processor sitting in this chair, and your main memory is sitting on the other side of the Neva River, somewhere near the Hermitage. So it takes a long time. If you want to read the memory, you ask someone to get on a bicycle and ride across the bridge and bring back the data. So really, you don't want to go to memory if you can avoid it. In order to communicate between the processors and the memory, we have in this case, it's a bus. In practice, it could be a network. Attached to each processor, we have caches. And the caches are the important thing. caches are really fast in the sense that a cache is like your desk. You can read and write to the cache in 1 or 2 instruction cycles. So it's literally hundreds of times faster than the memory. So when a processor wants, here the purple processor wants to read the blue data. So it broadcasts a message on the bus saying, I want that data. The memory says, oh, I heard that. And so then it sends the data to the purple processor. The purple processor puts it in the cache, and it marks it as exclusive, meaning that I know I have the only copy of this. So I can do anything I want to this without bothering anyone because I know that I have the only cached copy. Now, a red processor wakes up and says, I want to read the blue data. So it broadcasts a request, and the purple processor, which is much closer, says, wait a second, I have this, don't bother the memory. So the person in the desk next to you needs the same information. You hand over the piece of paper, or you copy the piece of paper and hand it over, instead of getting on the bicycle and going across the river. But at this point, we have to be careful. We mark each of these as shared. So that says that each processor knows that I have a copy of the data, but someone else might also have a copy of the data. So I have to be careful with this because I don't want to confuse others. Okay, now the red processor is going to write the data. So it writes new data. It doesn't really want to incur the cost and delay of going across the river, so it updates the copy in its cache, but it doesn't go to memory. But now we have a problem that we have 2 processes which have different ideas about what the data is. And so what happens is the red processor broadcasts an invalidation message saying, I just updated this address. If you have a copy of it, throw it away because it's no good. And then it marks that data as modified, also sometimes called dirty. So that says that at some point, the red processor has to write that back to memory, but maybe not yet. We'll be lazy about it. So this is all you need to know about how cache coherence works in a multicore. But the idea here is this cache acquires permission to write by taking away permission to read from everyone else. Now, here's how transactional memory works. It's similar, but not exactly the same. So here we have 2 processors, or they could be threads. And purple here says, I'm going to start a transaction. So it executes the begin transaction statement that I showed you before. And it says, I want to read this data. And this is marked transactional, which says that I read this data as part of a transaction. So that's not quite the same as reading it normally. And the green thread says, I also want to start a transaction. I want to read this. And the same thing happens. Now, purple decides it's going to commit. So what it does is it changes, I should put the letter here. All it does is it goes to its cache and it takes all the transactional bits and it clears them. It takes its cache and it blesses it, and all the transactional bits disappear. And it's as if it had read them normally. So that's very simple. So now when the green processor decides to write, it does the same thing. It marks it as transactional, and it marks it as dirty. So far, everything is almost exactly the same as in normal cache coherence. So let's rewind and see something more interesting. So let's go back to the situation where both transactions have read this data, and now green decides to write the data before purple commits. So green broadcasts an invalidation, and purple says, oh, wait, somebody just invalidated a transactional read. I've got to abort my transaction. I've got to throw away all my transactional data, reset my program counter to the beginning of the transaction. In this way, we can guarantee that all the reads and writes done inside of a transaction appear to be atomic by rolling back anyone who conflicts. Now, of course, there are many interesting issues here. How do we avoid starvation? How do we guarantee fairness? And so on. And there are many, many papers that people have written about this. But all I wanted to do here is convey the simplest idea and the simplest structure. But the key point is that committing a transaction is really easy, because when a thread decides it's going to commit, it looks in its cache and says, well, I went from beginning to end and there were no invalidations, no conflicts. Great, that's great. I win. I turn off all the transactional bits. And it looks as if it had done all of the reads and writes in the transaction normally, but without interruption. So retroactively it says, well, I managed to do all of this. There was no interleaving. I'm going to just accept it. And so I can go through and pretend, set everything to the status it would have been if I'd read this normally. And that's basically it. So we don't need distributed commitment protocols or anything of that nature. Now, as I mentioned, what I've described here is the basic principle behind existing hardware transactional memory systems like IBM's systems and Intel's systems. So what I'll do next, I'll give you a break right now, but what I'll talk about next is how you program Intel's RTM system. So Intel provides something called reduced transactional memory, which is basically a C library that allows you to access the hardware transactions. As you might guess from looking at this, the interface is a little strange. And the reason it's strange is because of the way the hardware is set up. So after I guess a 15-minute break, I will reveal the mystery behind programming these kinds of systems.